Okay, your next assignment is due on Tuesday of next week. Notice that for problem number 2, you only need to do parts A and B. I don't remember what the other parts are, but just the first 2 sections of that problem. And then on Thursday of next week, so a week from today, you need to submit your pipe network sizing draft. Here's a little bit new information about how to do that. I'm going to create a location on MU Online, just on the main page there, where it's an assignment and you can click on that and then upload PDF files. And so you don't need to print a paper copy of the maps. It'll be easier for me to take a look at what you've done if it's a PDF. And so when you print using water gems, select a paper size of 11 by 17 as you're setting up the page. And I show you how to do that in the videos that I've linked to previously. And then print to a PDF. So that's due a week from today. And just to sort of cover the old ground that I talked about last time on demand estimation, I want you to get the experience of rethinking your work and reviewing independently. But if you feel like you're choking and it's just not working and you're stuck at an impasse, please come see me, because I want you to struggle in a good way but not in a futile, frustrating way. So feel free to come see me if you need help on your demand estimation, or if you run into trouble on water gems. I'm happy to answer any questions that you've got on that program. So that submission's due a week from today. And then, looking a little bit further into the future, exam 2 is on Tuesday the 7th of April. So that's, all of this information is on that revised schedule that I gave you after our second snow day. After our second batch of snow days, but I just wanted to point it out. Today we're going to continue talking about the applications of specific energy and talk about discharge depth applications. So just to refresh where we're at, last time we looked at the specific energy diagram. And the specific energy diagram has on one axis the sum of the depth and velocity head. Here on the horizontal axis, that's the sum of the depth and velocity head. That's what we mean by specific energy, is we mean how much energy is there in the flow above the channel bottom. And then on the vertical axis, we have the depth of flow. And this curve illustrates the concept of alternate depths that was asked about in the quiz. It shows that for a certain specific energy, if we had 2 meters of energy in a certain flow, there's 2 depths that have that much energy. A subcritical depth up here and a supercritical depth down here. And this curve that's shown here would just be for some certain channel where we have a certain flow rate, a certain N value, meaning the roughness of the channel, a fixed channel width. If any one of these things were different, then we'd have a different looking curve. If you had more flow or if the channel width changed, we'd need to adjust the specific energy diagram. So what all of these different flow depths arise from is if we have varying slopes. If the channel slope is increased or decreased, that's what's going to govern the flow depth. Now, another way to look at this specific energy diagram is, what if we had, instead of a diagram that has a lot of different specific energies and varying depths, so here on this one that we've looked at before, specific energy is on the horizontal axis, depth is on the vertical axis. This figure is also presented in the text for a specific energy that is constant. And so what this is showing is that all of these different flow possibilities on this thick curve here have the same amount of energy associated with them, but there's some maximum flow rate that occurs for a certain amount of specific energy, and it happens to coincide with the critical depth. And so let's look back at the specific energy diagram and remind ourselves what critical depth meant on this curve. The critical depth was the depth where there was only one flow depth. It wasn't 2 of them. It's at this point, the farthest to the left here, the minimum specific energy for this certain flow rate. So critical depth here, when we were working through the example last time, I think it was 0.86 meters was that critical depth. And when we did the spreadsheet that had lots of different rows, we saw that the critical depth was associated with the minimum specific energy for a certain flow rate. So here's another way of looking at it. Critical depth is associated with the maximum flow rate you can get for a certain specific energy. So all of these different flow rate possibilities here, here on the horizontal axis we've got Q, which is flow rate. There's lots of different possible flow rates for a certain specific energy. But the maximum flow rate is what's corresponding to the critical depth. And so critical conditions are something very special. What we talked about last time was that on the specific energy diagram, the way that we conceived of critical flow was it's the minimum specific energy for a certain flow rate Q. But now what this curve is illustrating is that if you have a certain specific energy, and there's lots of different flow rate combinations that will give you that specific energy, the maximum discharge is associated with critical flow. So critical flow is a very efficient flow condition. It's how you can get the most flow through a channel for the least amount of energy, is for conditions to be critical. It's not particularly stable, but critical conditions are the way to get the most flow through the channel for a certain specific energy. And this is going to come up as we think about what happens when there's disruptions to uniform flow. One last thing to point out is that if you do take a look at this figure in the textbook, E, which is specific energy, this is showing that specific energy for each of these flow rates, different depths and flow rates, the specific energy is constant. And so think about where is the energy, what is the form, because specific energy has a component of, we could say, potential energy, which is the depth, y, and then the kinetic energy, which is the velocity head, v squared divided by 2g. And so think about when you're on this point of the curve. So this is saying you've got a low flow depth. So if everywhere on this curve has the same amount of specific energy, we know that if it's a low flow depth, there must be a lot of kinetic energy there to make up the balance. Whereas, by contrast, up here at the top, most of the specific energy is as depth, and so then there would be very low kinetic energy. And so where we can divide the specific energy diagram into a supercritical and a subcritical range, the same thing is true here. All of the flow conditions above this are subcritical, and below here are supercritical. We can divide that curve up into regions. All right, so this is where things get really interesting, and where specific energy diagrams and just the formula for specific energy allows us to solve some pretty interesting questions. So let's say that the water is flowing along, and it's uniform flow, normal depth here on the left. Y1 is just the normal depth that it would be. And suddenly there's a drop. This step here, delta Z, represents the channel bottom just drops down by some depth. And so what we want to know is, how is the water going to react to that change? We've added some energy there by having the bed drop down, and we are interested in trying to find out what is going to be the new depth downstream, Y2. So Y1 was the upstream depth that we knew. Y2 is this new downstream depth after the water goes over this step. And so trying to find out the new depth, is a multi-step process, and one of the first things we want to do is we want to try and find out whether conditions were supercritical or subcritical upstream. So question number one is, before the drop, what was the flow regime? Subcritical or supercritical? So in order to find that, we can either calculate the Froude number, and what Froude number is associated with subcritical flow? What's the dividing line? Less than 1, right, so 1's the dividing line, less than 1 means subcritical conditions, and by contrast, anything greater than 1 means supercritical flow. The other way that we can diagnose it is we can look at the flow depth versus the critical depth. And so, look at this. We don't have a Froude number on the figure, but we do have the critical depth is sketched out there. So can we tell just by looking at the diagram if the flow is supercritical or subcritical? We can. And what is it? Is it sub or super? What is it? Subcritical. That's right, Stephen. Why? Exactly. Yeah, the criteria that we covered last time in class is that when y is greater than yc, flow is subcritical. And when y is less than yc, flow is supercritical. And remember, I mentioned how maybe the names are a little bit, it's hard to remember because you'd think a deep depth is super, right? But really what's supercritical about shallow flow is that the velocity is really high. And what's subcritical about a deep depth, deeper than critical depth, is the fact that the velocity is moving slowly. So what we have here is subcritical flow that's pictured. So first of all, just when we're doing the calculations, when we're crunching the numbers, we may not have a drawing that makes it obvious to us whether it's subcritical or supercritical at 1. So we have to either calculate the critical depth and compare depths, or calculate the Froude number and see where it is relative to 1. Now, once we find out whether it's subcritical or supercritical, we could solve this graphically by going to our specific energy diagram. And so I'm going to step you through a very crude animation that shows how you could find out what the new depth is. First thing we'd do is we'd start with our initial flow depth, y1. So that is given in the problem statement, what the initial depth is. So we would go over to the specific energy diagram from the axis, from the y-axis, over to the specific energy diagram. Where it intersects the curve, that's where we'd go down to however much energy there is at 1. This is the graphical approach, but we can do the same thing numerically. We'll follow essentially the same steps. We'll calculate what is E1. We'll know the depth component, and we'll know the velocity head component, and find how much energy is there above the channel bottom at location 1. Now, from this intercept of the horizontal axis, we're going to go to the right in the amount of delta z. And the reason why we're going to the right is how much energy is in the water has actually increased because of that step. The water was up high. Think of it this way. The water was elevated some amount, and when it flows over the edge, it's gaining energy, the specific energy. It's not gaining total energy, but remember, specific energy is just measuring how much energy is in the flow above the channel bottom. And since the channel bottom is now lower, that means that the water is going to have more energy than it did before because it's flowing over the edge there in the amount of delta z. So we have a new amount of specific energy. This E2 is simply however much was there at 1 plus the drop, the delta z. So there's more energy at 2. Any questions so far? Everybody's following the steps here? Okay, we've got more energy. So now we simply go up, and this is where we need to know whether conditions were subcritical or supercritical, because when we go up from 2, you'll notice that we're crossing the specific energy diagram in 2 spots. We're crossing the diagram at our supercritical crossing and our subcritical crossing. And so we needed to know whether it's sub or super at 1 because it's going to stay in the same flow regime at location 2. So at location 1 in this illustration, we know that it was subcritical conditions just because of what Stephen said, that the depth y1 is greater than the critical depth. So that tells us this is the depth that we should use. You know, these are the two options. It can either be this one or that one. And it's the deeper of the two because this deeper depth corresponds to the subcritical depth. And so finally, we go from that curve over towards the vertical axis again, and that's our new depth y2. So the depth actually gets deeper because of this step downward, because of the drop-off. If it had been supercritical flow at 1, then the depth would get shallower. Yeah.
That change is not just delta Z, it's actually
Yeah,
crazy.
that's right. Yeah. So y1 is measuring from the bottom of the channel to the water surface. And what we see is that y2 is deeper than y1. And it's not y2, sometimes students look at it and think, well, y2 is simply y1 plus delta z. And that's not it. There's actually a little bit more to it than that. The velocity changes as well.
Does
Yeah.
the kinetic energy not change from the first depth to the second depth?
No, it does. It does. Yeah, because if you've got more depth, then the velocity is also going to change. Yeah.
So that,
The flow rate, now let me point out that the flow rate at 1 and the flow rate at 2 are still equal.
is that why equation 3, like equation, the part of step 3 there where E2 equals E1 plus the delta Z,
Mm-hmm.
it just like, for some reason I'm just thinking that would be only an increase in potential. Like it's stepped up just by that factor.
Well, the specific energy is the sum of the kinetic and the potential. And so how much energy did you gain is all because of the delta Z, but it puts some of that energy into additional depth and it puts some of it into,
Right, I was
The-
thinking again that the Y2 is just Y1 plus the
yeah, it's more than that because this is a curve. If it was linear, then that's all it would be. But because it's curved, there's sort of a nonlinearity there that means that both the velocity head is changing and the depth is changing. So we'll do some specific calculations to illustrate that with this example. All right, so we have same picture as before. You can tell just by looking at it that it's subcritical, but we're going to go further than that. We're going to not just rely on the picture. We're going to actually calculate whether conditions are subcritical or supercritical. And the way I'm going to do it is by calculating the Froude number, as I illustrate these on the board. We've got a rectangular channel. The bottom width is 8 feet. The depth at 1 is 3.5 feet. And now here's a cross-section at location 2. We don't know what the depth is. I think it's probably going to be deeper because I know from the picture that it's subcritical, but let's not make that assumption. Let's actually just do the calculations here. So this is a bed drop example. All right, so we've got, here's our channel, 8 feet wide. The flow rate is 30 cubic feet per second. And at 1, Y1 is 3.5 feet. And the delta Z, that step down, is 1.2 feet. Okay, so the first thing I want to do is diagnose the flow regime. The Froude number at location 1, so I'm saying FR subscript 1, Froude number at location 1 is going to be the square root of Q squared times the top width divided by G A cubed. Okay, so we'll plug in the numbers there. The flow rate is 30 cubic feet per second. The top width is easy since it's a rectangular channel. The top width is always going to be 8 feet regardless of what the depth is. G in traditional units is 32.2 feet per second squared. And then the cross-sectional area, we're talking about at location 1, area is 3.5 feet times 8 feet. So that area is 28 square feet. 28 feet squared. And we cube that. And then all of this is to the 1/2 power. Okay? So the Froude number is 0.101 subcritical flow. By the way, Froude number is unitless. So there aren't any units associated with that 0.101. Oh, yep, thanks. It is. Yep, 30 feet squared. Right. Okay, so any questions so far? Why do I want to find out at the very first whether the flow at 1 is supercritical or subcritical? Right. Because whatever it was before, it's going to be after. It was subcritical before, it'll be subcritical after. Okay. So now here in step 2, I'm going to start considering the specific energy. I'll say that the energy at 1 plus the delta Z is how much energy there is at 2. In other words, Y1 plus V1 squared divided by 2G is equal to Y2 plus V2 squared divided by 2G minus delta Z. So I just moved the delta Z from the left-hand side of the equation to the right-hand side of the equation. And in this case, I can find out what V1 is. It's Q divided by A1. So the velocity is going to be the 30 cubic feet per second divided by 28 square feet. My velocity is 1.071 feet per second. So I can start substituting all the information that I know so far. I don't know the velocity at 2, though, because I don't know the depth. So this is going to be one of those cases where I substitute in a different form of velocity head. Instead of having it in terms of V2, I'm going to write Q squared divided by 2G A squared. And the A that I'm talking about is whatever the depth at location 2 is. Okay, so you'll see what I mean by that in just a second. Okay, so it is 3.5 feet, which was the depth at 1, plus 1.071 feet per second squared, divided by 2G, which is 32.2 feet per second squared, is equal to Y2 plus 30 cubic feet per second, and that's squared, divided by 2GA squared. So 2 times 32.2 feet per second squared. And then I don't know the A in terms of number, but what I can do is I can write it in terms of some unknown depth. So it is 8 times Y2, and then the area is squared. And then delta Z is minus 1.2 feet. So any questions so far? Charles?
I got it.
It was where what came from? Y1? Okay, yeah. So what you'll see is I've only got one unknown in the equation. It's the depth here, Y2 is unknown. And then in the velocity head, I'm expressing the velocity head in terms of whatever the depth ends up being, Y2. Okay? So let me combine things around a little bit. What I have is 4.718 feet is equal to y2 plus 0.2184 y2 squared. Okay, and then that rearranges into y2 cubed. If I multiply each term by y2 squared to get it out of the denominator here, so I multiply all of the terms by y2 squared, then I'll have y2 cubed minus 4.718 y2 squared plus 0.2184 is equal to 0. And I need to find the roots of this equation. And so the three possible solutions for y2, it is either negative 0.211, 0.220, or 4.708. Those are the three possible flow depths for this amount of energy. Okay, we can obviously eliminate the negative flow depth. That doesn't make any sense. And so we've got a supercritical depth to choose from or a subcritical depth to choose from. And what we know from the very beginning is that at location 1, conditions were subcritical, so the flow is going to stay subcritical at 2, and this is our new flow depth. It'll be 4.708 feet. So that's the flow depth after the drop. So how much did it drop down? 1.2 feet. And so if we had the mistaken assumption that y2 is just the drop plus the original flow depth, we would have said 4.7, but this is 4.708. You know, there's a little bit additional depth that comes from the fact that the velocity is slower at location 2. Okay. Any questions about that example? All right. So that's a step down. What if we step up? What if there's some sort of an obstacle? Now the delta z here, it's a little bit more complicated because a step down, the water can always flow over the edge of something. It doesn't really matter how big the delta z is. The water's going to be able to continue flowing. But in this case, that step up delta z possibly could be so high that it interrupts the flow, that it becomes kind of like a wall. You know, if you've got a really big delta z, then you've essentially put a wall in the middle of the channel. And, you know, can the water flow over the wall? So let's take a look at this. It's many of the same principles. We've got a location 1, which is upstream, a location 2, which is downstream. You can see from the figure here, they're showing the TEL, total energy line. The total energy stays constant through that transition, but we're going to solve this on the basis of specific energy, not total energy. Remember, specific energy is how much energy is in the water above the channel bed. So at location 1, there's a certain amount of energy in the water. And you can think of that as like your currency. It's how much energy you've got to get up over the obstacle. It's how much energy there is to continue flowing in spite of the step up. So the specific energy does change just like it did with the step down, but here the specific energy, instead of increasing, it's decreasing. And so E2, which is the specific energy after the step up, is E1 minus delta Z. So instead of plus, which it was with the step down, now it's a minus, since it's a step up. And how are you going to remember that? Well, you could either just memorize it or think through it logically that there's going to be less energy at 2 than there was at 1 because the water's having to get up over that obstacle delta Z. So E2 is going to be lower than E1 was. The total energy doesn't change. You see that line up on the very top there is constant. The difference between total energy and specific energy is that total energy is measuring the energy relative to a datum that's horizontal and fixed that doesn't change with the channel bottom. And so total energy maybe would be some imaginary dashed line here that's horizontal. And so even though we may have less depth here, the delta Z stays in the total energy calculation. So here's our specific energy diagram. And trying to find the new depth can be solved graphically or numerically, like we did on the whiteboard. So let's just think through the graphical approach here. What's illustrated here is it's showing that the depth decreased. You can see, here Y1 is pretty deep, right? And Y2 is less deep. So let's look at the specific energy diagram and convince ourselves why the water would do that. So here's Y1, the original depth. We go over, down, and we find E1. That's the specific energy that's associated with what the original flow depth was. Now instead of moving to the right, which means more energy here, we're moving to the left when we intercept the horizontal axis. So E2 is E1 minus delta Z. So that's where this delta Z here is. It's deflecting to the left, lower specific energy. So we go back up to try and find our new depth. We've got two possibilities. We've got a supercritical and a subcritical. And we can, depending on the Froude number or comparing the depth originally at 1 to the critical depth, we can find which of the routes to use. Assuming that conditions at 1 were subcritical to begin with, then this would be our route. And what you can see is that the depth is lower. So here's the really counterintuitive thing, is that there's an obstacle there. Delta Z is an obstacle, and so the water, after the obstacle, is moving faster. It has a higher velocity. So think about continuity is Q1 and Q2 are equal. The flow rate's the same. Water isn't accumulating between 1 and 2. We know that whatever flows in has to flow out. This is steady flow here. It's non-uniform, but it's steady, which means flow in equals flow out. Since the depth is lower at 2, the velocity has to be higher. So that's the sort of counterintuitive response that the flow has to a step up. This obstacle is that at location 2, the velocity is greater. Brandon?
Why doesn't the water surface respond in a similar way as it did when delta Z decreased instead of increased?
Well, it's because it's losing energy instead of gaining energy. And so the response when there was a bed step down was the depth got deeper. And this was subcritical flow. All of the answers really are in the specific energy diagram. And so when you had more energy, you were on this side of the curve, which made it deeper. But we're not gaining energy. Gaining energy means that your E is getting bigger, but our E is getting less, and so that puts us lower on the top part of that curve. The water surface here, it increased. Here, it's lower, yeah. The water surface is lower. Y2 is less. Okay, yeah.
If our initial conditions were supercritical,
Yeah.
why would
Good. So that's what's illustrated here. Let's say, what if it was supercritical to begin with? So let's take a look at the specific energy diagram. If you've got a step up and it's supercritical conditions, then yes, Y2 downstream is going to be bigger rather than smaller.
Is there a place where the water surface elevation would remain the same? For an obstacle?
For an obstacle?
Is there a depth?
I don't think so.
Or will it always respond in one way or another?
Yep. I guess that's the exception, but the water would have to, if it's flowing critical and there's an obstacle there, then it will have to pool upstream before it can flow at critical again after the obstacle.
We cannot change from sub to super the other way around.
Not if at 1 and 2 the channel slope's the same. Because that's one of the things that's assumed is that there's a step up or a step down, but it's the same roughness. It's not like you're going from a smooth surface to a rough surface. It's the same channel width. It's the same material type and it's the same slope. It's just that there was a step up or a step down. Other questions? There is a limit to the delta Z that the flow can handle. So if you've got a really big delta Z, then you don't have enough energy to get over the obstacle. So one of the ways that right here, when I said E1 is the energy available to push the water, the flow, over the step, if you've got a really big delta Z, you may not have enough energy at 1 to get it over that obstacle. So we'll talk about in a minute what happens when you don't have enough energy to get over the obstacle. We will get to that. It's a really interesting thing that the water does. Before we do, I'd like us to similarly, we did an example having to do with a step down. I'd like you to do an example having to do with a step up. So you can pair up with a partner, somebody sitting near you. And here's what we know. At location 1, the channel is 10 feet wide. The flow depth is 5 feet. At location 2, we don't know what the depth is. It's the same slope and the same width, though. We have a flow rate of 250 cubic feet per second. And then the step, this is a step up, is 0.5 feet. So I'd like you to calculate what is the flow depth after the step. It's the same process as it was before, but E1 is E2 plus delta Z instead of minus delta Z. E1, yeah, that's right. E1 is E2 plus delta Z, right. Now, you can find out, this first thing that you do where you're diagnosing the flow regime, you can do it one of two ways. You can either do the Froude number approach or do comparison of depths. Either one is fine. Okay, so I'll turn you loose to work on that. We start off by diagnosing the flow regime at 1 so that we can know which of the routes to pick later on when we solve the routes. So the question is it subcritical flow or supercritical flow at 1? And what I did was I went the route of calculating the critical depth and then comparing Y1 to the critical depth. It would have been fine if you calculated the Froude number instead. Either way could give you the answer you need. So when I did that, I found the flow per unit width. That's what this lowercase q is the flow rate divided by the width of the channel. The units are a little bit weird. It's feet squared per second, or if you think of it better this way, it's cubic feet per second per foot. So 25 feet squared per second, put that into the equation for critical depth, find that the critical depth is 2.69 feet. And you can see from the comparison that I put on the board there, since that 2.69 feet of the critical depth is less than the given depth of 5 feet at Y1, then that means it's subcritical flow. So any questions with diagnosing the flow regime, just to do the preliminaries there? Okay, so this is, I started off by just finding out what's the specific energy at 1. It's the depth and the velocity head, so 5.388 feet at location 1. And then what we know is that the energy that's at 1 is energy at 2 plus delta Z. The other way to think about that is E2 is E1 minus delta Z. So there's going to be less energy at 2 than there was at 1 because of the step up. So I put in some of the particulars here, the total energy at 1, the height of the step up of 0.5 feet, and then the depth and the velocity head. The velocity head is best expressed in problems like this in terms of Q and A, because we only want to have one variable, or one unknown. We want to have our unknown be y, in terms of y, instead of not knowing the velocity or the depth. And so writing it in terms of Q and A is convenient because we already have our unknown variable being y here, and so that when we substitute in the flow rate and G and so on, we have the cross-sectional area in terms of the 10-foot wide width and the unknown depth y2. So the rest of it is just rearranging algebraically and then finding the 3 roots of the equation. So any questions with that part of it? So Eric, how do we know which of these 3 roots to choose? Yes, it would. But how do we know? You feel it. Sometimes that's all it takes, right? What about if it was in the brain rather than in the gut? Okay, all right. So let's step through. Let's first eliminate this. We know it's not the negative flow depth because that doesn't exist. Charles, what were you going to say? Yeah. You know, even if you didn't already know this is the subcritical depth and this is the supercritical depth, you could put these possibilities in the Froude number equation and find out, you know, which of these is the subcritical root and which one is the supercritical root. And that would eliminate any doubt. Or we could just sort of remember that the bigger of the 2 depths is going to be the sub. So this is the subcritical root, this is the supercritical root, and our rule is if it was sub before, it will stay sub after. And so our new depth at location 2 is going to be 4.383 feet. Okay. Uh-huh. Oh, you're talking about the height of the water itself?
Yeah, from Y1 to Y2, if Y1 was 5 and Y2 was 1.7, that's up to fall 3 feet at drop.
That would be a pretty extreme case, wouldn't it? All right, let me just refresh your memory that you can calculate the critical depth for any channel using this formula, but rectangular only for this simplified version of it. One of the unique things is that when you've got critical flow, the depth is 2/3 of the specific energy when it's critical conditions. And we're running a little bit low on time, so I'm not going to prove that to you. But let me just put the number up on the whiteboard there. For this example, what it ends up showing is that if you've got 50 cubic meters per second, Q equals 50 cubic meters per second, and the channel is 5 meters wide. If you have critical conditions for critical flow, it works out that the critical depth in a case like that is 2.168 meters if you solve for the critical depth using that rectangular formula there. Well, the specific energy is 3.252 meters. And so that depth is 2/3 of the specific energy. That's just sort of a unique aspect of critical flow, is that 1/3 of the energy is in the form of the velocity head, and 2/3 of the energy is in the form of the depth. And so sometimes if we know that the conditions are critical, we'll just solve E for critical flow is 3/2 times the critical depth. This is like a little simplified formula you can use to find the specific energy when you know conditions are critical. One place that you know conditions are critical is over the top of an obstruction that's very tall. The water depth will pool until it reaches critical flow. So it's this relationship that actually allows you to use a broad-crested weir as a flow measurement device. If you know conditions are critical, then you can use it to solve for the flow rate. We won't get into that right now, though. We will talk about it when we go back and do one of the first lab demos. Okay. Before you finish for today, we still got some time. So why I didn't want to go through this example is I actually wanted to give you a preview of what we'll talk about next Tuesday. And that is what if the bed step gets too deep? So just to review what we talked about today with a step down and a step up, when it's a step down, that step down can be infinitely large without it affecting the upstream flow. But if you have a delta Z that's too big, then it can choke the flow, because remember, the E1, however much energy you have at 1, is what you've got available to get up over the obstacle. So let's just take a look at this. This is a small delta Z here. The delta Z for condition A is small, and so if it was subcritical at location 1, this delta Z made the flow depth go down a little bit. That's what happened when it's a small step up. Okay, this next step up is a little bit bigger. So what happened? Well, you've got a more extreme divergence between Y1 and Y2. You know, here in this first case, Y1 and Y2 were pretty close because delta Z was small. But now, Y1 and Y2 are getting further apart. You know, the Y2 is a bigger, more exaggerated drop in the depth because of that step up. So there is a limit to how big of a step you can have and still get the water up over that obstacle, and that is, we call it the critical step, delta Z sub C. It's so big that now it's the last depth that the water can get over that step, and it's when it has critical flow over the obstacle. At the beginning of the lecture, I told you that critical flow conditions are very efficient. And what it is it's the maximum flow rate for a certain specific energy. And so the flip side of that is it's the least amount of specific energy for a certain flow rate. So before the water starts backing up at 1, what it'll do is it'll flow at critical conditions over the step. But if we raise the step even further, so now here in condition D, we made that step up even bigger than it was in C. Now what you can see is that the water had to respond upstream. At location 1, there simply wasn't enough specific energy to get over that obstacle. And so the water had to pool and pool until it had enough specific energy to get over the new obstacle. And so it was accumulating energy at location 1 in order to have enough to get over this big obstacle. And the way it accumulated energy at 1 was by pooling. And so it was gaining additional depth, additional potential energy, until it finally had enough specific energy to get over this obstacle. And so that's where we're headed when we get together next Tuesday. We're going to talk about the case of a maximum step and trying to find out how big that maximum step limit is and what happens to the flow when it pools upstream. And we're going to introduce some new notations. You know, there's Y1 and Y prime 1, where Y1 was the original flow depth before it pooled, and Y prime 1 is the new flow depth. And so what we'll be asking next Tuesday is, you know, how much is it going to pool before it can finally get over that obstacle? All right, so we're out of time. I'll see you on Tuesday. Have a good weekend.